by Dr. David Ruppert and Dr. Patricia Steinhilber. I just added a couple of updates and the new logos. One of the updates is this legalese slide. The Extension Service is funded by federal funds. Has anyone seen this slide before? One person. Okay, we need to do this better.
Chuck showed it this morning.
Chuck showed it. Oh, okay, then you all have seen it before. Basically, it is our responsibility because we are federally funded to serve everyone equitably in the state of Maryland without any discrimination. If you encounter discrimination in an extension program, there is a process by which you can report that to the USDA, which is detailed here. And it also just tells you about our responsibilities to accommodate any needs that you have to participate fully. So just to wake you up real quick and to help me know who I'm talking with, how many of you have farming experience? Okay, how many of you have taken a soil science class before? Awesome. How many have taken a soil fertility class before? Pretty good, okay. So this is good. Some of this will be mostly refresher for those of you who've taken this before. For those of you to whom this is new, just be aware that between Erica and myself, we're covering 2 or 3 semesters worth of material in a couple hours. So if you feel overwhelmed, it is not your fault. There's a lot of material that we're covering. But please ask any questions that you have. So what we're talking about today is soil fertility, but the bigger picture is what limits crop production, what stops your crops from getting as big and as healthy and producing as much food as possible. Water, there are many limiting factors that will limit your crop production. Water, air below the ground, CO2 in the atmosphere, the temperature, mechanical support that the soil provides. You know, when it rains and all the trees fall down, that's the mechanical support of the soil failing when it gets too wet. The nutrients in the soil, disease and pest pressure, and symbioses. And what we're talking about today is just the nutrients, just the basic soil fertility. But all of these factors affect your crop production. And I mention this because sometimes growers come to us in extension and they say, you know, my crops are not growing well. What fertilizer do I need to add? And then we have to tell them, well, let's look at the problem. Is it a fertilizer problem? And sometimes it's not a fertilizer problem. In this photo, what we've got is phytophthora blight of peppers. And it doesn't matter how much fertilizer you add, that's not going to solve the phytophthora blight problem. So as advisors, it's important to be aware that there are other problems out there that might be causing your clients the challenges that they're seeing. But today we're talking about soil fertility. So what is the definition of a nutrient for a plant? It's something that is required to complete their life cycle, and it's exogenous. That means that the plants can't generate it for themselves. So sugar, for example, carbohydrates is something plants need to complete their life cycle, but they make those carbohydrates themselves by taking the energy from the sun, by taking the water and the carbon and putting them all together. But nutrients, the things that we add to the soil, or that manure adds to the soil, or organic matter adds to the soil, are things that the plants can't make for themselves. They have to be obtained from the environment. One kind of fundamental plant fertility concept is the Liebig-Sprengel law of the minimum. And this is a very old metaphor for how soil fertility works on plants, with the idea that if you've got a barrel of water, like a rain barrel, you know, they used to be made of wooden staves. Let's say these staves are made of different lengths. The water in the barrel is only going to rise up to the lowest stave, and then it's going to run out that hole. So if your pH is in the wrong zone, if you've got a pH of 4.5, say, it doesn't matter how much phosphorus and nitrogen you add, the water's still going to stay at the level that the pH allows it to be at. And this is a very useful concept, but there are some limitations to it because it assumes that the nutrients and the other factors don't interact with each other. But it also is very useful when growers come to me and say, hey, the fertilizer salesman has come to my farm and he says I really need more boron and other micronutrients, and we're going to add brown rock. And then I say, well, let's look at your soil test. Is your pH good? Do you have enough phosphorus and potassium? What's the water like in your soil? And if those are not doing well, if those are limiting your plant's growth, it doesn't matter how many micronutrients you add. those micronutrients won't do you any good if the other factors are limiting your growth. There are a lot of plant essential nutrients. Memorizing them is a fun rite of passage for all of us. Some of them are considered non-mineral, and we're not really going to talk about them much today: carbon, oxygen, and hydrogen. And then we break them up into the mineral macronutrients, which are the ones that are required in large amounts, and the micronutrients, which are the ones that are required in small amounts. And one concept that we talk about a lot is that holding charge is holding nutrients. And that's because if you note, it's a little hard to see up on the screen, but I've highlighted the negative charged molecules in yellow and the positively charged ones in green. Most of these, all of these mineral nutrients have a positive or a negative charge associated with them. And most of them have a positive charge. There are a few that have a negative charge. And that means that they are looking for their opposite charge, and that's what attaches them to the soil, which we're going to talk about a lot today. So having space to hold on to those positive and negative charges is what allows your soil to hold on to these nutrients. There's I always struggle with pronouncing this word, mnemonic for essential plant nutrients. And it goes, there we go. CB Hopkins Cafe Company, closed Monday morning and night. See you Zoom the management. For those of you who've studied this before, can anyone point out to me some of the nutrients, the essential nutrients that are hidden in this mnemonic? Anybody see anyone? You can shout them out.
Carbon.
Carbon, there we go, there's carbon. What do you think the B might be? Boron. Hydrogen. And this one actually has a lot in Hopkins. There's an O here for oxygen. What do you think this one is?
Phosphate.
Phosphate. Potassium. And then I'm going to cheat and give us the code. The N is nitrogen. The S is sulfur. The Ca in cafe is calcium. The Fe is iron. The Co is cobalt. The Cl enclosed is chlorine. The Mo in Monday is molybdenum. The M and N in morning are manganese. The N and I in night are nickel. Cu is converted into letters because we had a little trouble squeezing it in. So that's Cu for copper. There's the Zn for zinc and the Mg for magnesium. And I always get mixed up. The abbreviation of magnesium is Mg, manganese is Mn. So it takes a little while to wrap your head around this, but if you're having trouble remembering the long list of essential nutrients, this is a trick for memorizing them. And you do have that in your slides. I'm pointing at the wrong place, that's the problem. There we go. So what do plants do with these nutrients? They play indispensable roles in the machinery of how the cells in the plants function. Basically, the plants take these nutrients up through their roots, and they use them to build their bodies and move around all the pieces inside their bodies that they need. Nitrogen is really important for making proteins. Phosphorus helps with moving energy around and building DNA. Potassium helps with the salt balance between the roots and the soil. Magnesium is an essential element in chlorophyll. As you can see in this figure, chlorophyll shares a lot of the chemical structure with hemoglobin, which is the molecule that moves oxygen around in our blood. And in hemoglobin in our blood, the center of the molecule is iron. In plant chlorophyll, the center of the molecule is magnesium. So magnesium is just as important to plants as iron is to us for our health. So there are three main questions that we're going to try to answer today in the soil fertility part of our class. One, why are some soils better at supplying nutrients than others? Two, how do soils lose nutrient content, and how can you tell that they've lost it? And three, what can you do to maintain the fertility of your soil? So let's start with why are some soils better at supplying nutrients than others? All things being equal, why are some soils just better at this, more fertile than others? The start of the answer that we're going to flesh out over the next few slides is that some soils just contain more nutrients to start with. And then some soils hold on to those nutrients better when you add them, or the ones that they start with. So why do some soils inherently contain more nutrients to start with? Because our soils develop from different geologies. The soil is just basically ground up pieces of rock, tiny, tiny pieces of rock. And if you imagine that, classic Nature Channel documentary where the volcano comes up out of the ocean and then over millennia, that beautiful black volcanic rock gets crumbled by the waves and the wind and the rain into little pieces of soil and the plants grow. That's where our soil came from. The rock is formed in different ways. There's volcanic rock, there's rock that's been crushed down by pressure, there's rock that's been laid down by the sediment in rivers, so it gets formed in different ways, but once it's formed, then it breaks down over millions of years into tiny, tiny pieces of sand and silt and clay, and the plants then grow in that. So how it's formed and what materials it was formed out of affects the nutrients that start out in that soil. Here is a table of some examples of different minerals, and minerals are kinds of rock. And if you think about those essential plant nutrients that we just talked about, you can start to spot that these molecular formulas here, here's the name of the mineral, here's the molecular formula of that mineral. Some of these molecular formulas have more of those essential plant nutrients than others. So the quartz is made of silica and oxygen. And oxygen is essential, right? But the plants get plenty of oxygen from the air. They don't really need oxygen from rocks. Silica is increasingly recognized as important for rice and grasses, but it's not needed in large quantities, and there's a lot of it available. So soil that's based on a quartz parent material doesn't have a lot of starting nutrients for your plants. That's one reason why sandy soils, which tend to be made of a lot of quartz that's been ground down, just don't have as many nutrients to start with. Then we start going down to other kinds of soils, olivine, kaolinite clay, for example, aluminum, silica, oxygen. Again, not a lot of plant essential nutrients. Montmorillonite has calcium, has magnesium. Limestone has magnesium. Muscovite has potassium. That's fluorine, so that's not really a hugely important one. So montmorillonite is one of the ones that has more nutrients to start with than some of these other minerals. And then, of course, limestone has lots of calcium and tends to have a very high pH to start with. Then, accounting for the rock that the soil came from, why do some soils then hold on to more nutrients? And this is where we get into soil chemistry. And I know chemistry is not everyone's favorite subject, but I will tell you that I hated chemistry in high school. I tolerated it through college, and then I got to grad school and I got to take soil classes and crop science classes, and it suddenly became interesting because the chemistry of soil and plants affects how our plants grow, it affects how our bodies digest things, it affects how nutrients move through the soil, and it's a lot cooler when you can see how those chemistry concepts affect things that matter to you. So if you feel like, oh no, we're talking about chemistry, please stay with me. I promise it's more interesting than it was before. So some soils hold more nutrients because they differ in organic matter content. They differ in the relative amount of sand, silt, and clay, or soil texture, which Erica just talked to you about. And they differ in the relative amount of different kinds of clays. They differ in pH. And all of these soil properties affect the ability of the soil to hold on to nutrients. Soils can be made up of different components, and those components have a different ability to hold a positive charge. Organic matter in this table is highlighted in the top in black because it has by far a much larger ability to hold a positive charge than the other types of material that might be in your soil. Vermiculite clay and again montmorillonite clay hold a lot of charge. But as Erica pointed out, if your soil is entirely clay, you've got other problems to deal with. And then you start getting back to that Liebig's barrel, right? Where maybe water or aeration might be limiting more than the nutrients. And then as you go down the table, silts And sands have very little ability to hold positive charge. So overall, soils that have more clay, more organic matter, and more of certain kinds of clays. Notice there are several clays on this table and they vary in their ability to hold on to nutrients. So soils that have more clay, more organic matter, and more of certain kinds of clays like vermiculite and montmorillonite, those hold more positive charge because holding on to charge is holding on to nutrients. So because all soils typically have a distribution of sand, silt, clay, and organic matter, all soils have some ability to hold nutrients. It's very rare to be growing an entirely beach sand. That is something we deal with sometimes out on the eastern shore. But in general, across Maryland and across the US, soils are a mix of sand and silt and clay with some organic matter. This table talks about by soil texture class, the amount of charge held per weight of soil. And this is, the units are centimoles per kilogram, so that's centimole of charge per kilogram of soil. And this is specifically about positive charge, not negative charge, or milli equivalents per 100 grams. And the thing to remember about these two is that they are the same, they're just at a different scale. It's thinking about like gallons versus cups. The centimoles per kilogram is the big volume, and the milli equivalents per 100 gram is the little volume. So why does soil texture affect the soil's ability to hold on to these nutrients? And if this is, some of you, you may be familiar with this, but I just want to take a step back because I think this is a really important concept. So I like to say that soil texture is like family. You get what you get and you're stuck with it unless you move somewhere else. So it's probably the most important soil property you have to learn about and deal with. And when you hold a handful of soil in your hand, it all kind of looks similar. And it's hard to see with your naked eye the difference between sand and silt and clay. You might be able to see a few extra large grains of sand. You can kind of feel it even better with your fingertips. But if we were to shrink ourselves down to the scale where this matters to your plant roots, to the microbes in your soil, if we were to shrink ourselves down so that a drop of dew in the morning or a drop of mist in the morning or fog was the size of a basketball, then a piece of sand would be about the size of the building that we're standing in. And a piece of silt would be about the size of this table that Kayla's sitting at, and a piece of clay would be about the size of this projector advancer. So at the scale where your plant roots and the nutrients are interacting with the soil, these soil textures are so humongously different that it has huge effects on the chemistry and on the ability of the soil to hold on to nutrients. The other reason why those size differences matter is a concept called surface area to volume ratio. And my biology professor used to harp on this for a whole semester because he liked to say that surface area to volume ratio affects almost every basic concept in biology that you have to deal with. And it's a little hard to wrap your head around at first, but the basic idea is that large objects like sand, we just talked about sand is the biggest texture class, they have a lot of surface area because they're big, right? But they also have a lot of interior space. So their surface area divided by their volume is relatively small. But if you take the same amount of volume, like say we've got one piece of sand the size of this building, then the surface area is all of the outside of the building divided by the inside. That's the surface area to volume ratio. But let's say instead of one piece of sand the size of this building, you had the volume of this building filled up with these projector advancers. And then the surface area is all the surface area of all of these little projector advancers, or in this case, you've divided up into cubes. And the surface area is all of the surfaces of all of these cubes added up together. And the volume is still the same, but you have a lot more surface area. So you just got a lot more space on the outside of the objects. And this matters for your soil's ability to hold on to nutrients because all of that space on the outside of the soil particles is where the nutrients stick to. That's where that charge is that the positively charged nutrients stick to. So the more surface area there is in the soil, the more space there is for the nutrients to stick. And this starts to get into the concept of cation exchange capacity that Erica mentioned. And this is another one that people sometimes run up against and then they just have trouble wrapping their head around it. So I like to think about cation exchange capacity as like the parking lot. in your soil. We've all been to a restaurant that's an awesome restaurant. You really want to go there, but their parking lot is this big, so they can just only have so many customers. Whereas, you know, maybe Applebee's is kind of meh. It's kind of good. It's okay. You know, it's got the same thing you want every time, but they have a huge parking lot, so it's really easy to get there. So they have lots of customers. So cation exchange capacity is kind of like that. It's got the more cation exchange capacity your soil has, the more space it has to park nutrients and hold on to them. And in this picture, you know, imagine the nutrients are the cars. Those empty spaces aren't actually empty. They're usually filled with hydrogen cations. So when there's an empty space when there's a space on your soil particles that's not filled with a nutrient, it's usually filled with hydrogen, either because the plant, as in this picture, exchanged hydrogen for a nutrient with the soil, or because the soil solution, the water in the soil, just had hydrogen in it, and that exchanged with the nutrients on the soil surface. So clays, the smallest soil size texture, they attract positive ions because negative charge is built into them. By their molecular structure, they have a negative charge to them when they're formed. And when they're formed, there's a process called isomorphic substitution that we're not going to get into today. I don't think that's going to show up in your exam, but that's where the charge comes from. And clays attract positive ions that then go sit on those negative charges. So basically think of clay as a very negative little magnet, and you've got these positive little magnets of nutrients floating around, and they stick onto the negative charges on the clay. And because, as we just talked about with surface area to volume ratio, clays have a lot of surface area, so they've got a lot of this negative charge for stuff to stick to. Positive charges, which attract the negative ions, and remember there are some negative nutrients like nitrate. Those are rarer in clays, except for iron oxides. So those negatively charged plant nutrients tend to stay in the soil less. They're easier to leach out with the soil water than the positively charged nutrients. There's less space for the soil to hold on to them. There's fewer parking spaces for those negatively charged ions, those negatively charged nutrients. The ability of the soil to hold charge or to hold nutrients is called its ion exchange capacity. The ion exchange capacity overall is the amount of charge that can be retained by a certain amount of soil mass, a certain number of kilograms or grams of soil. And these are the units again that we use to measure the ion exchange capacity of soil: centimoles per kilogram, which is the same as milliequivalents of charge per 100 grams of soil. Here we go. Cation exchange capacity, then the ion exchange capacity is broken up into two categories: cation exchange capacity. Cation refers to positively charged ions. So cation exchange capacity is the soil's ability to hold on to positively charged ions, like potassium. And anion exchange capacity is the soil's ability to hold on to negatively charged ions, like nitrate. Organic matter and most clays have a whole lot of cation exchange capacity, and iron oxide clays are the only ones that have a lot of anion exchange capacity. So clinging ions on the soil come from the soil water, and they can go back to it. So there's this constant exchange happening with the soil water and soil particles, where these ions, they're not forming really strong molecular bonds. They're just kind of floating together like magnets that are kind of stuck to each other. It's not like you're gluing a bumper sticker on your car. It's more like those magnetic bumper stickers that can peel on and off. So we have a special term for the soil's ability to hold the charge, and that's exchange capacity, which we just talked about. And the nutrients will float, the ions will float back and forth in the soil water, between the surface area of the soil particles, and between the root hairs. And roots exude cations, like hydrogen, that they then use to kind of change the balance and force the nutrients on the soil particles off of the soil into the soil water where they can take them up. All right, so there are these two kind of pools of nutrients in the soil water, and that's all plant available. It's easy for the plants to get to. When they suck up the water, the nutrients come to, or they can use these active ports on the soil, the cells of the roots that can trade nutrients back and forth. The soils attached to the soil solids are a little bit less available to the plants than sorry, I just said the same word twice. The nutrients on the soil solids are less available to the plants than the nutrients in the soil water, but they're still eventually available. They will eventually exchange back and forth between the soil water and then to the plant. And the plant can affect that release by pumping cations into the soil water, kind of changing the balance and knocking them off the soil. Cations in the soil water are dissolved cations. Cations absorbed to the soil are the cation exchange capacity. That's a measure of the cation exchange capacity. And these, you can test both of these. Soil fertility tests measure the cations that are on the soil. Anions, the negatively charged ones, they can dissolve in the water, and they can be adsorbed, stuck to the soil particles, and that is a measure. If you measure all the negative charges attached to the soil particles, that's a measure of anion exchange capacity. Hydrogen also can dissolve and float around in the water. That's the active acidity. That's how acid the soil water is. And in fact, it's the pH of the soil water slurry. When you put soil in a little vial, you add some water, you smush it around, you stick a pH probe in, that's what you're measuring when you measure pH that way. Hydrogen that's adsorbed or stuck to the soil particles, that's the reserve acidity. So when you get a soil test back, sometimes it will tell you about the active acidity and the reserve acidity. The active acidity is how much hydrogen is floating around in the soil water. The reserve acidity is how much hydrogen is stuck to the soil particles. So if you add calcium or lime to the soil and it knocks the hydrogen out of the soil water, that reserve acidity will throw more hydrogen from the soil into the soil water and slow down how long it takes for you to change the pH of your soil with limestone. So that's why those two measures are important and different on your soil test. And a buffer test will tell you about the reserve acidity. So those are two different soil test methods and two different numbers you'll get on your test results. Generally, cation exchange capacity is larger than anion exchange capacity. Soils can hold more positive charge than they can hold negative charge. And exchange capacity overall is larger than dissolved ion content. So there's more positive and negative ions stuck to the soil than there are floating around in the water. All right, now we're getting into some of the math that you might encounter on the test. So exchange capacity is a routine analysis that some soil testing labs will offer. Most commonly, they'll report to you your cation exchange capacity. That's just the positive ones. But you can also request the exchange capacity in total. Here's an example where, excuse me, you got some results that it tested the entire positive charge. So this is the cation exchange capacity. The exchangeable positive charge was extracted and measured on a per kilogram basis by a soil testing lab. And they found that there are 3 centimoles of positive charge coming from hydrogen that was stuck to the soil, 12 centimoles that came from the calcium that was stuck to the soil, 5 centimoles that came from the magnesium that was stuck to the soil, 1 centimole came from the sodium, and 4 came from the potassium. So what is the cation exchange capacity of this soil? Any guesses on how we would calculate that? If you want to jump out, you can, or I could just, okay, I won't put you on the spot. But cation, it's really easy, luckily. The cation exchange capacity, you just add up all of these positive charges, 3 plus 12 plus 5 plus 1 plus 4. That gives you 25 centimoles of positive charge. And then you divide it by kilograms per kilogram of soil. So we already know that the results were in a per kilogram basis. So our cation exchange capacity is the total of all of these positive charges. That's the 25 centimoles of positive charge per kilogram of soil. And if you want the test wants the results in milliequivalents per gram, 100 grams, 1 centimole per kilogram is exactly equal to 1 milliequivalent per 100 grams. So 25 centimoles of positive charge per kilogram is equal to 25 milliequivalents of positive charge per 100 grams. So any questions about that before we keep going? Okay. How am I doing on time? It is
11:39.
okay, excellent. So while nutrient content can be tested, we can also evaluate the share of the ion exchange capacity that's occupied by certain elements. And this is particularly of interest. People tend to be particularly interested in how the percent of the adsorbed elements that are not, quote, acidic. And so this includes a definition of acidic that's beyond just hydrogen at pH. There are some cations that are considered acidic, and they're all kind of grouped together on the periodic table. Hydrogen, aluminum, iron, and manganese are the ones that we're concerned about. And then there are some cations that are considered basic or alkaline. Calcium, magnesium, sodium, and potassium are in that group. And if you look at, let's see. So this then, when you see on a soil test a measure called base saturation, that's what this is talking about, is the amount of essentially parking spaces on your soil that are occupied by these 4 cations, calcium, magnesium, sodium, and potassium. So the base saturation is the share of the cation exchange capacity that's provided by basic cations. And this is of interest because if we think about that parking space image from earlier, you know, you've got that parking lot where some of the spaces are occupied by cars and some of them are occupied by hydrogen ions or some of these other acid cations. Iron and manganese are nutrients, aluminum is not. So this matters because it's useful to know, yeah, hey, you've got a lot of cation exchange capacity, but how much of that cation exchange capacity is actually filled right now by these base cations that are really useful to your plant? Yes? Yeah, absolutely. So this is the formula for calculating base saturation, and you calculate it by summing up the centimoles of positive charge per kilogram that come from magnesium, calcium, sodium, and potassium, and then you divide it by the cation exchange capacity. And we're going to work through an example of this. So people use it for gauging soil fertility. I meant to talk about what I just talked about with this. So it's a gauge of soil fertility because it's a measure of how many of your parking spaces, it's not exact. It's a rough measure of how many of your parking spaces are filled up with really useful cations. So let's work through how you would calculate it. So back to our previous example, we've got information about the positive charges that come from hydrogen, calcium, magnesium, sodium, and potassium in your soil. We calculated the cation exchange capacity by adding up all these positive charges per kilogram of soil. We got 25. So what's the base saturation? The base saturation is the centimoles of positive charge that come from the base cations. And then we have to go back to this table. Which are the base cations? Calcium, magnesium, sodium, and potassium. And if we look at the cations that we found out are on our soil, got calcium, magnesium, sodium, potassium, and the only one that's not a base cation is hydrogen in this example. So how we calculate it is we add 12 from the calcium, 5 from the magnesium, 1 from the sodium, and 4 from the potassium, and divide it by 25 from the cation exchange capacity. So the top of this positive charges from these basic cations, and the bottom of this fraction is the cation exchange capacity that we just calculated, or that was given to us on the soil test. So we have 22 divided by 25, and you can go back and check. The only nutrient, the only cation that was acid was hydrogen, so that's 3. That's the difference between the top of the fraction and the bottom of the fraction, so that means we added our numbers up correctly. 22 divided by 25 is 0.88. And to get a percent base saturation from a decimal, you multiply the decimal by 100, so then you get 88%. 88% base saturation. So if you get a base saturation result on your test, this is how they calculate it. Or not on your soil test. I'm sorry, I'm talking about soil tests, the test you're going to take. So if you get a soil test back and it tells you about your base saturation, this is how they calculate it. If you get a question on your exam that looks like this about what is the base saturation of this soil, you might want to memorize calcium, magnesium, sodium, and potassium are the basic cations, and then you should be able to calculate it from there. So remember, cation exchange capacity is the sum of all of the positive charges, and base saturation is the sum of the positive charges from calcium, magnesium, sodium, and potassium divided by the cation exchange capacity. All right, any other questions about base saturation? All right. So in review of this section, soils with more organic matter and more clays hold more nutrients, and that is because of the geology, clays, and the management that you as an advisor or as a farmer do to your soil. So the more organic matter you build up, the higher the soil's ability to hold nutrients, and the better you reduce erosion, the better you take care of your soil, the better your soil's ability is to hold nutrients. Because the more eroded your soil is, you tend to lose those nice little particles first. The beautiful topsoil gets washed away first, and you get left with more gravel and more parent material and less ability to hold on to nutrients. So add organic matter, prevent erosion, that increases your soil's ability to hold on to nutrients to a certain point. I work with a lot of growers who create their own soils essentially by bringing in materials in high tunnels on top of soils that are heavily eroded in the city. And sometimes people grow in mostly compost, and then you get into a whole different category. So if you're in that situation, we should talk some more, because stuff gets weird. But if you're working on most like a traditional mineral soil, you know, it's been eroded, you add some organic matter, maybe you get it up to 3% or 4%, that's doing really good. Nutrient holding capacity is the exchange capacity, the ability of the soil to hold on to charges, both positive and negative. Cation exchange capacity is the ability of the soil to hold on to positive charges. Anion exchange capacity is the ability of the soil to hold on to negative charges. And cation exchange capacity is larger in almost all soils than anion exchange capacity. A kind of rough snapshot of the nutrients in the soil is base saturation. And pH, I don't know why that's summarized here, because we're going to spend about 17 slides talking about pH next. Yeah, so I'm going to skip that review. All right, I think we have some time and lunch is not here, so I'm going to keep rocking and rolling, and we're going to talk about pH. So what is pH? It's a measure of acidity versus alkalinity. It's a spectrum. And alkalinity is kind of interchangeable with basicity. I'm not quite sure how to turn that into an adjective, but alkaline and basic are kind of interchangeable, the same word. We just use them in different contexts. pH is a shorthand for the number of dissolved hydrogen ions, positive cations, hydrogen ions that are in the soil water. So an acidic soil has more abundant hydrogen and fewer hydroxyl ions, the negative ones. If you look at these two, the cation and the anion, if you stuck them together, that should make a very familiar molecular formula. What happens if we stick these two together? What do we get? Water, yes. So this is just water that's been split in half into the positive hydrogen and the negative hydroxyl. Alkaline soils or basic soils have a lot of the hydroxyl and not a lot of the hydrogen. And they kind of play a zero-sum game. They balance each other. This is just saying the same thing, but with a picture. At the acidic end of the spectrum, there's a lot of hydrogen. At the basic end, there's a lot of hydroxyl. The range that we're looking at with soils is like around here. At the more extreme ends of the pH range, you get into things like stomach acid at the very acidic end, or bleach at the very basic end. And something that I find helps me remember why pH works the way it does is if you think about a solution like stomach acid that's got a whole lot of hydrogen cations floating around, all of those hydrogen cations are looking for their hydroxyl counterpart. They are looking for a negative charge to balance themselves out. So if you stick your hand in stomach acid, your skin's going to get burned because those hydrogen cations are going to rip the negative charges off your skin. And the same thing at the other end. At the very basic level, if there are a lot of negative charges floating around and not a lot of positive, then those negative charges are looking for a positive charge to balance themselves out. So that's why if you soak your hands in bleach, your skin gets burned because those negative charges will rip the positive charges off your skin. So that's what pH is. It's a gradient between these positive charges and negative charges. That's the conceptual level. Then we start to get into math. pH is a negative log of the concentration of hydrogen cations. And logs are not my favorite part of math, but they're really important to pH. And the way to understand how logs work is that a logarithm is an exponent. So if you think about, 2 to the second power, that's 2 times 2, that's 4, that's an exponent. And so this table here, shows here is the actual concentration of hydrogen cations in moles per liter. Mole is a very large number. It's like a dozen, but really, really large per liter. So it's the count of these hydrogen cations per liter. And if there are 0.1 moles per liter, then that's 10 to the negative 1 is the exponent that you can use to express this number. And so when there's a negative exponent, it just means you take this number here and you move the decimal over 1 or 2. 1, 2. Decimals here. That's what this negative 1 is referring to. Here you've got negative 2, so it moves it over there. So it's basically a way of converting this number that increasingly gets a long string of zeros into a smaller number. That's what these exponents are for. And the thing to remember here is that as the pH number is smaller, like a pH of 1, there's a lot of hydrogen ions. And it's kind of counterintuitive. Like you think about if a number is large, that should make it more acidic, right? But it's the opposite here because it's a negative log. So the lower the pH, the more acidic it is, the more hydrogen cations there are. But the way that helps me remember is that means at the higher end, there's more hydroxyl ions because it's a spectrum. It's not just about the hydrogen ions. So at this end of the pH scale, at the lower numbers, there's a lot of hydrogen cations floating around and very few hydroxyl ions. And here at the higher end at 9, there are very few hydrogen cations and there are a whole lot of hydroxyl negative ions floating around. That jumped 2 slides. So why this matters is that you can't manage nutrients without managing pH. After soil texture, which is maybe the most important soil property, I would argue that pH is maybe the second most important because it affects so many things, especially for soil fertility. And this graph here. There's a lot of versions of this out there. I've heard some arguments that the phosphate bar here should actually get a little thinner higher up than it does in most of these graphs. But the important concept is that there's this, the thickness of each bar in this graph is the availability of the plant nutrient to your plants. So it's not how much there is in the soil, it's how available it is. So if we look at magnesium, for example, between 5.5 and 7, the bar is thickest. That means there's the most amount of magnesium available for your plant roots to take up. If you go further down to a pH of 4.5, the bar gets thinner. That doesn't mean there's less magnesium, it's still there. It's just bound so tightly to the soil particles that your plant roots have trouble ripping it off. And the same thing at the high extreme end of the spectrum at 8. So this is why when your soil pH is too low or too high, it doesn't matter really how much fertilizer you add, because almost as soon as you add it, it gets stuck to the soil, it gets bound up into these other molecules, and your plants can't get it. So if you've got good soil test phosphorus, but your pH is wrong, that's why it doesn't help to add more phosphorus, but you have to focus on changing the pH instead. The other problem with extreme pHs is that at the really low pH levels, some of the toxic elements start becoming more available to your plants, like aluminum, and then you start getting aluminum toxicity. In areas with other kinds of soil contamination, like lead, it's not on this chart, but lead also becomes more plant available at low pHs, like 4.5. All right, so in general, we want to keep our pH between 6 and 6.5, maybe 5.5 and 7, the wider end. And there's a note that nitrogen fixation is in legumes, beans, is facilitated by a slightly acidic to neutral pH, so maybe more like 5.5 to 6. And we're going to go over that on another slide. So pH affects not only the nutrient availability, which we just talked about, but it also affects cation exchange capacity and anion exchange capacity, because when you have higher acidity, and again, that's lower pH numbers, that higher acidity will lower the cation exchange capacity and the base saturation, because there are more hydrogens floating around. That leaves fewer spaces for the nutrients that your plants need, because hydrogen is not a plant essential nutrient, but a lot of other positive charges are. So the more hydrogen there is, the more acidic it is, the less space there is for your other nutrients. Target pHs we're aiming for in Maryland. Alfalfa establishment is an outlier. We want that to be up around 7 of pH 7. Tobacco, there's less and less of that growing, but it's still around some. You want pH of 5.6. A few crops, horticultural crops, potatoes, sweet potatoes, and blueberries want pH that's a little lower, like 5.2-ish. And most agronomic crops, corn, soybeans, and most horticultural crops, tomatoes, broccoli, want a pH around 6.5. In general, over time, pH tends to go down, with the exception of high tunnels. I work with a lot of high tunnel growers, and depending on what you add to that high tunnel and the pH of your water, you can sometimes see the pH going up in high tunnels. So if you're growing outdoors, generally you worry about your pH going down. If you're growing in high tunnels, you sometimes worry about your pH going up too high. So in review, most crops have a target pH of about 6.5. pH is a negative log base 10 of hydrogen cations, and more hydrogen cations means lower pH, means less abundant hydroxyl. They balance each other out. They're kind of a zero-sum game. And it means a lower cation exchange capacity and a lower base saturation. So as you're studying for your exam, I would recommend going back to these review slides and going back to any of the slides where you do some math, because those are probably things that are going to come up on the exam. All right, so how is soil fertility lost? We talked a lot about where soil fertility comes from in the geology and how the soils hold on to nutrients. But how do we lose the soil's ability to hold on to nutrients? And how do we lose the nutrients from the soil? What do you see happening in this photo? Anyone notice any problems? Erosion. Yeah, so this started out as a grass waterway where they got a lot of water flow, but you can see the grass has kind of been either washed away or covered by soil. And this could happen because of large rain events in the winter when you don't have a crop, maybe no cover crops holding onto the soil in the winter. It can also happen from plowing and tillage, because if you manage your tillage improperly, you can gradually move the soil from the higher parts of the field to the lower parts of the field. And as that soil erodes, as we talked about earlier, you're losing the physical space in the soil for nutrients to stick. You're losing cation exchange capacity. You're losing your topsoil. And you're also losing the nutrients that are in that soil. Like Chuck talked about earlier, that soil that gets eroded away has nutrients in it, and that's going somewhere it doesn't. It will hurt things away from a place where it is helping things. So erosion is the big one. But other than erosion, how do soils lose their ability to supply nutrients? So we're going back to this table that we talked about earlier. Remember that soil-based nutrients are ionic. They have positive and negative charges. Remember that ions or nutrients, they dissolve in water or they stick to the charges in the soil. So there's those two pools of nutrients, the nutrients that are in the water, the nutrients that are stuck to the soil. And that means good things and it means problems as well. So when nutrients are dissolved in the water, the plant roots can then, it's good that because the plant roots can pull those nutrients out of the soil water easily into the plant roots, and that makes them quickly available to your plants. The downside of that, though, is that those dissolved nutrients can be easily leached out of the root zone. And in Maryland, we have a pretty humid climate. We get 43, 45 inches of rain a year. Further out west, they're lucky if they get 20. Some states only get, 12 or 15. So we have a pretty humid climate with a lot of rain, a lot of snow. And that means we tend to lose the nutrients that are floating around in the soil solution, because every time it rains, it pushes that water further down into the soil, below the plant root zone, below where your plants can get to them. And this loss through being leached away may be the fate of up to 50% of the nitrogen we apply. And that's why we've been harping on for years, and you've probably heard this many times already, it's better to apply nitrogen as close to when your plants need it as possible, because many of the nitrogen ions are negatively charged, so there's less space in the soil for them to stick to. Here we go. Nitrate, negatively charged, and that's a big negative charge too. So it takes a lot of negative charge on the soil to hold on to that. So nitrate just doesn't stick to the soil very well. It's easily leached out by the water. And that's why we've been harping on this idea of apply nitrogen as closely as possible to when you need it, apply it in slowly available forms. It used to be really popular. I used to work out in Minnesota. People would buy anhydrous ammonia in the fall when it was cheap, and they would inject it in the soil in the fall, and they'd have all winter to leach away. So we recommend not doing stuff like that. Applying nitrogen in the spring, applying it close to when your crops need it. All right, then on the side of the nutrients that are stuck to the soil, those nutrients, the good side of that is the nutrients can be held by the soil to be made available to plants later. It's kind of like your pantry. You've got stuff there that can be used later. The downside of that is that some nutrients can be held so strongly that the plants can't get to them. And again, that happens when you have soil pH that's too low or too high. There are also some molecules like iron that can bind really tightly to some plant nutrients. And when those nutrients get high enough, they can bind up your plant nutrients and make them less available. Phosphate, this tends to happen to at extreme pHs. But then if we think about some of our soils that have really high phosphate levels, like really high on the phosphorus index, sometimes the phosphate, as you might notice, is a negative charge. And it's a larger negative charge than the nitrates, 3 negative charge. So if the soil phosphate gets high enough, like really high on the phosphorus index that you're going to use a lot in your nutrient management planning, then even phosphate can be lost through leaching in the soil solution. Because all of the negative charges that are available in the soil are already occupied by phosphate, so it doesn't have anywhere to go, and then it goes to the soil solution and it gets leached out. So this leaching and binding is another method by which nutrients, the soil can lose ability to supply nutrients. Another way that the soil can lose ability to supply nutrients, and I'm seeing Dwight in the back. I'm assuming lunch is not here yet. Okay. Shucks. Okay, I'll keep going then. I'm sorry. There's nothing to distract you quite yet. So nutrients can change form. They can change from their plant available ionic forms to gaseous forms that then volatilize out of the soil. And again, this is where we talk about nitrogen, because nitrogen changes forms a lot. This is why nitrogen will not show up on your soil fertility tests. Because if we go out today and, it's going to be a dry week, so it's a little different, but let's say we go out today, we collect a soil sample, we send it off to the lab, it gets stuck in traffic, it goes around through the post office, it gets to the lab, maybe 4 days, a week later, it gets in line to be processed, they process it, they test it, they send you the results back maybe another week later. And in those 2 weeks, you've had another 2 or 3 inches of rain. That's washed the nitrate out of the soil. That's turned some of the nitrogen back into ammonia, and it's volatilized back up into the atmosphere. So the nitrogen in your soil today is completely different than the nitrogen 2 weeks ago when you took the soil sample. So that's why you don't get a number for nitrogen generally in your soil test results, because it changes too fast to be usefully analyzed by soil testing. So in this picture, what we're seeing is yellowing and dying plants that were caused by waterlogging. So when the soil is waterlogged, the nitrate, bacteria transform the nitrate back to N2, the gas form, and N2O. And then those gases go back up into the atmosphere. And sometimes the plants in the field, in those low spots, they're killed by a lack of oxygen in the soil, because their roots can't get oxygen to grow with. But then the plants that survive tend to develop a nitrogen deficiency because the soil has lost the nitrogen to the air. So there's this double whammy that happens when soils get waterlogged. Nutrients can also interfere with each other's uptake or form insoluble compounds. And we talked about that a little bit with phosphorus a minute ago. Here's a table of interferences that can happen between nutrients. So this column is the nutrient that is in excess. That means there's a lot of this nutrient. And when that nutrient is in excess, this column tells about the induced deficiency. So for example, if there's a whole lot of calcium floating around, your plant can have a deficiency of potassium. Even if there's plenty of potassium in the soil, water and on the soil cation exchange capacity, because there's so much calcium that there is competition between the calcium and the potassium to be taken up by the plant. And this is another example of where Liebig's law of the minimum gets a little more complicated, because even if potassium is not the most limiting nutrient, there's plenty of it in the soil, it can become limiting because there's so much calcium that the calcium fights with the potassium to get up into the plant. And the same thing happens here with, if there's too much potassium, then magnesium can have an induced deficiency, and down through this chart until we get to phosphate, where there's a different mechanism for the induced deficiency. So if there's a lot of phosphate, then it can bind to iron, manganese, zinc, and copper, and form these insoluble compounds that the plants can't break apart with their roots. And so if there's way too much phosphate, that can cause a deficiency of iron, even if there's plenty of iron in the soil, because the phosphorus and the iron bind together so tightly. Yes?
Can you speak to plant deficiency and different pH levels, like
Yeah. So I definitely don't know all of them, but I have observed in the field phosphorus deficiency at high pH. Even like 7.78, I've started to see some phosphorus deficiency in plants. Symptoms, perhaps. Um, but then I would have to go back to that table of that's on one of your slides about pH. And that, there we go, slide 39. So that one pretty much shows the deficiencies you would expect to see at the low and the high pH. But so based on this table, at the low pH of like 4.5 to 5, that's when aluminum, iron, and manganese become available. And so aluminum you don't want your plants to take up because it's toxic. So the thicker the bar, the more available it is. And the thinner the bar, the less available it is. So at really low pH, the nitrogen might be less available because the bar is really thin there. So you might observe nitrogen deficiency symptoms at really low pHs. You might observe phosphorus deficiency symptoms or molybdenum deficiency or boron deficiency. And that gets really complicated as well when you're looking at the symptoms because a lot of these nutrients become less available at low and high pHs. So you start to see multiple symptoms showing up together. And then there can also be just general stunting because the pH is so low that it can damage the plant roots, and the aluminum toxicity can start to show up. So we're going to cover a few slides on the symptoms that plants show when they're nutrient deficient, but it's rarely as clear cut as some of the examples that we like to show. The concept here, though, is that soils that have an excess of one particular nutrient can cause a deficiency in another nutrient. And high levels of phosphate and high levels of calcium tend to be the ones we see frequently. Over time, soils in humid environments, that's us in Maryland, tend to become increasingly acidic, taking you out of that sweet spot of like 5.5 to 7, 6 to 6.5, with the exception of high tunnels, which are weird. My favorite topic. So the one on the slides was 6 to 6.5 pH. Oh, I don't know where I'm going. Here we go. 6 to 6.5 is the sweet spot. I tend to work with growers who are working in kind of suboptimal conditions. So if their pH is between like 5.8 and 7, I'm like, that's good. Don't worry too much. But if you are like trying to hit your maximums, like if you've got a lot of, if you're really optimizing your management, 6 to 6.5 is really where most people want to be. But it does vary depending on what crop you're growing. So most agronomic and horticultural crops, corn, soybeans, tomatoes, broccoli, 6 to 6.5 is where you're looking. But there are some exceptions like potatoes and blueberries, which like a more acidic pH, and alfalfa, which likes a really basic pH up around 7. Other questions? So where does the soil acidity come from? Nitrification of ammonium. So this is important when you add ammonium fertilizer. There's a process that happens in the soil where that ammonium becomes nitrate, which is plant available, but that process adds hydrogen cations to the soil and increases the acidity, makes the pH number lower. So the more ammonium fertilizer you add over years, the lower it drives your soil pH. And that, again, is more important in more controlled environments like high tunnels because there's less other factors changing things, but it is also important in field-based production as well. Most fertilizers and all organic sources of nitrogen provide nitrogen in an ammonium form, so they cause this reaction, this acidification of the soil. Plant roots and microbes release organic acids. to knock the nutrients off of the soil, which we mentioned a little bit earlier in that cation exchange capacity slide. So those plant roots will kind of push out hydrogen cations and other organic acids into the soil to force the nutrients off the soil so that they can then suck them up. And over time, this will slowly decrease the pH, increase the acidity of the soil. Rainfall can decrease the pH, can increase the acidity because of carbonic acid, nitric acid, and sulfuric acid in the rainfall. This is the phenomenon known as acid rain, where it's not as bad as it used to be. We've actually done a pretty good job of solving this problem. A lot of our power production used to put a lot of carbonic acid, nitric acid, and sulfuric acid into the air. That would then rain back down onto the soil and acidify the soil. And we've cleaned up a lot of those smokestacks, so there's a lot less, the rain is less acidic than it used to be, which is good. There's still a little bit of natural acidity in the rain. There's still some smokestacks that are putting out sulfuric acid, but it's better than it used to be. So we're seeing less acidification of the soil from the rain than we used to. Oh, and here we go. Here's the graphic of the plant roots putting out hydrogen cations and knocking the cations off the soil. Let's see, there's also the transformation of geologic minerals into soil minerals. That happens very slowly, but over time as your soil weathers, it can also become more acidic. And the oxidation of sulfur. And this is most important when you have soil that's too basic. So let's say you're growing in a high tunnel, you're adding well water from a calcium well, or you're adding municipal water from Baltimore City. That will increase your soil pH over time. You maybe need to decrease it then. Maybe you end up with a pH of 7 or 7.5. You see it increasing over time, and you need to knock it back down to have the best production in your high tunnel. You can do that by adding elemental sulfur. There are other forms of sulfur like gypsum that will not change your soil pH. So if you need to change your soil pH, gypsum won't do it. You need elemental sulfur. And there are some fact sheets out there where you can calculate how much elemental sulfur to add depending on what your soil pH is to lower the pH. But in most situations, people tend to worry about the soil pH being too low, in which case you need to add lime to bring it back up. Another important cause of soil infertility is if the soil material is too high in carbon, it can rob the plants of nitrogen. This is something that you probably don't deal with a lot on agronomic farms, but on horticultural farms, I do see people using really high carbon mulches. And that could be useful on the soil surface, but if you till it into the soil, it can start to steal the nitrogen out of the soil away from your plants. This graph here shows the carbon to nitrogen ratio. So the thick end here, more carbon, less nitrogen. The thin end here, less carbon, more nitrogen. 25 to 1 is kind of the line between if you have a larger carbon to nitrogen ratio, say 60 to 1 or 80 to 1 or 400 to 1, like sawdust, then nitrogen will be immobilized. So if you take sawdust and or some wood chips, a lot of the horticultural growers I know love wood chips because they can get them for cheap. If you use them as a mulch on top of the soil, that's great because it will help with the weeds. It will steal the nitrogen from the weeds on the surface of the soil. It won't hurt the soil down below. Over time, it will decompose and create organic matter. Very good. But if you then mix the wood chips into the soil, microbes will break the wood chips down. And as they break the wood chips down, there's so much carbon that they need nitrogen to balance out that carbon, so they'll pull nitrogen from elsewhere in the soil to break down the carbon in the wood chips. And that will suck up the nitrogen in the soil and cause nitrogen deficiencies for your plants. So please do not mix wood chips into your soil. On the other end of things like mature alfalfa hay, finished compost should have a carbon to nitrogen ratio of 15 to 1. If you ever have a grower ask you to look at their compost analysis, this is what you're looking for. You want a carbon to nitrogen ratio less than 25 to 1, closer to 15 to 1. Microbial biomass has really low carbon to nitrogen ratio. All of these will mineralize nitrogen, will provide nitrogen as a source to your soil. And the higher the carbon to nitrogen ratio, the slower it decomposes. The lower the carbon to nitrogen ratio, the faster it decomposes. So the takeaways, if you've got a material with a higher carbon to nitrogen ratio than 25:1, use it as a mulch on the surface. If you've got a material with a carbon to nitrogen ratio of lower than 25:1, that can be a good nitrogen source. You can incorporate it into the soil. If you're looking at a compost analysis, what you're looking for is 15:1 or thereabouts, if you're using it as a soil fertility amendment. All right. So how can nutrient deficiencies be determined? How do you figure out you've got a deficiency? What do you think? Should we keep going, or should we let people stretch that?
I finish.
Finish. How many slides do I have? I have about 15 slides left. Keep going. Finish.
Yeah.
Okay.
Push through.
We'll get you on the road faster, maybe. All right. So how can nutrient deficiency be determined? Visual symptoms. Note the location and type, and this is where we're going to talk a little bit about what you asked about. Your slide's printed in black and white, so it's not the best example, but there are some really good guides out there on the internet for different crops, and the symptoms will vary depending on what crop you're growing. I've seen really good ones for corn. I've seen whole book really good ones for tomatoes. So the more commonly grown crops, you can usually find nutrient deficiency symptom guides like this. And this is kind of one of the older classic ones. What you tend to see with nutrient deficiency symptoms is different colors other than green showing up in different locations. And symptoms might not all be caused by nutrients, right? Here's an example of chemical burn on corn leaves where you've got kind of these necrotic regions on the edges. There can be diseases, these little spots. If you get spots like these, then I call up my buddy Andy Mess and I say, help, there's a disease, I don't know what it is. Drought causes leaf curling, but then you start to see these kind of funny stripes, some of them in between the veins, some of them in like a V shape. Some of them are yellow, some of them are purple, and depending on the color and where it shows up on the leaf and on which leaf it shows up, that tells you which nutrient is deficient. Is that the lunch has arrived? All right, we're going to stop here. We need a break. We'll come back. All right.